Hi, I'm Hunter, and if tech confuses you, that's about to change. Your earbuds, your car, your smartwatch, your fitness tracker, the wireless keyboard you type on, the heart rate sensor on your gym equipment, all of them run on the same technology. And almost nobody knows where that technology got its name. Bluetooth is named after a Viking king, a literal 10th century Danish king named Harald Bluetooth, who united warring tribes in Scandinavia. And the logo, that little angular symbol you see on every wireless device on Earth, is a monogram of his runic initials, H and B, fused together. A 1,000-year-old king's signature is sitting right there on your AirPods. That was supposed to be a temporary code name. The engineers picked it while they were building the technology, assuming the marketing team would come up with something better before launch. They never did. The code name shipped, and now it's everywhere. That detail tells you something real about how Bluetooth actually developed. Messy, improvised, constantly patched and rebuilt from the ground up. And knowing that history explains why the Bluetooth in your phone today is almost unrecognizable from what launched in 1999. So here is every major Bluetooth version, what changed, why it mattered, and what is quietly happening right now that most people have no idea about. It started in 1999. Bluetooth 1.0, 1 megabit per second of raw speed, a range of about 33 feet, and this is the part nobody talks about. It barely worked. Devices from the same manufacturer often could not pair reliably with each other. The spec required hardware addresses to be transmitted openly during pairing, which meant there was zero anonymity. Anyone in range could see your device. Early Bluetooth headsets would drop connection mid-sentence. Printers would refuse to handshake. Engineers spent more time debugging connections than using them. Version 1.1 cleaned up some of those pairing bugs. But the real fix came with Bluetooth 1.2 in 2003, and it introduced something that still runs silently in every Bluetooth device today: adaptive frequency hopping, AFH. Here is what that means. Bluetooth operates in the 2.4 GHz band, the same band as Wi-Fi, microwave ovens, and a stack of other wireless signals. When those signals overlap, you get interference. Bluetooth 1.2 solved this by making the radio constantly jump across 79 different channels, 1 MHz apart, at a rate of 1,600 hops per second. 1,600 times every second, your Bluetooth device is jumping to a new channel, learning which ones are crowded, and avoiding them. You are never sitting on one signal. You are constantly moving. That is why Bluetooth and Wi-Fi can coexist in the same device without drowning each other out. Bluetooth 2.0 launched in 2004, and it brought EDR, enhanced data rate. The raw throughput jumped to 3 megabits per second. But the counterintuitive part is that it actually used less power than 1x, even though it was moving more data faster. The reason is straightforward. Faster transfer means the radio finishes the job and turns off sooner. Less time transmitting equals less power consumed. Consumer electronics finally got behind it. Your 2006-era Bluetooth headset ran on this. Then came Bluetooth 3.0 in 2009, which is one of the most misleading spec sheets in tech history. The headline number was 24 megabits per second. Huge leap, right? Except that speed was not actually Bluetooth. Bluetooth 3.0 added a feature called high speed, or HS, which worked like this. Bluetooth negotiated the connection, figured out what needed to transfer, and then handed the actual data off to a Wi-Fi channel. The 24 megabits was Wi-Fi doing the lifting. Bluetooth was just the middleman. Almost no manufacturer ever implemented it. It stayed on paper. The real story of 2009 to 2010 was happening somewhere else entirely. Bluetooth 4.0 launched in 2010, and this is where everything changed. Not because of speed, because of a second protocol that lived inside the same frequency band but worked completely differently. BLE, Bluetooth Low Energy. Most people assume BLE is just regular Bluetooth with the power turned down. It is not. BLE is a separate protocol. It shares the 2.4 GHz frequency with classic Bluetooth, but it has different packet structures, different connection logic, and a completely different design philosophy. Classic Bluetooth was built to stream continuous data, audio, files, real-time communication. BLE was built for something else. Devices that wake up, fire a tiny burst of data, and go back to sleep. Think about what a temperature sensor does. It sits there. Once a minute, it wakes up, sends a number, and goes quiet again. A fitness band counting your steps does not need a constant stream. It accumulates data and sends it in small bursts. BLE was designed for exactly that pattern. The power numbers tell the story. Classic Bluetooth draws somewhere between 1 and 100 milliwatts. BLE draws 0.01 to 0.5 milliwatts. That is not a small difference. Some BLE sensors run for over 2 years on a single coin cell battery, a CR2032, the kind that costs less than $1. 2 years of continuous operation on that. Apple used Bluetooth 4.0 as the foundation for iBeacon in 2013. Small BLE transmitters placed in stores, airports, and stadiums that could push location-aware notifications to your phone. Walk past a gate at the airport, and your boarding pass pops up. That was BLE doing the work. Bluetooth 4.1 in 2013 was mostly about one problem: 4G LTE. Both LTE and Bluetooth operate near the 2.4 GHz band, and when LTE traffic spiked, Bluetooth connections would stutter. Version 4.1 added coexistence logic to coordinate the two radios so they would not step on each other. Not glamorous, but if you ever used a Bluetooth device on an older phone and noticed it dropping when you got a call, that fix is what you were waiting on. Bluetooth 4.2 in 2014 brought two things worth knowing. First, it gave BLE devices IPv6 support, meaning a tiny sensor could hold its own internet address and communicate over IP networks directly. That opened the door for smarter IoT infrastructure. Second, and more importantly for everyday users, it introduced privacy mode. Earlier Bluetooth devices broadcast a fixed hardware address, like a Wi-Fi MAC address. Anyone passively scanning could see your device and track your movement. Version 4.2 added randomized address rotation, so your device's address changes periodically and becomes much harder to track across time. Your phone today still runs this feature every time its Bluetooth radio is on. It also increased BLE packet size from 27 bytes to 251 bytes, about 10 times larger. More data per burst without more connection overhead. Bluetooth 5.0 landed in 2016 and it moved fast. Within a year, it was in the iPhone 8, iPhone X, and flagship Android devices. The specs were straightforward. Double the speed of BLE, 4 times the range in open space, theoretically up to around 800 feet, and 8 times the broadcast message capacity. The range increase sounds dramatic, but in real-world indoor use, walls and interference cut it down significantly. What actually mattered for most people was the combination of doubled speed and the cleaner LTE coexistence added through the slot availability mask feature. Connections were more stable. Audio had fewer dropouts. The underlying plumbing was just better. Bluetooth 5.1 in 2019 added something genuinely new: direction finding. The spec introduced two methods, angle of arrival and angle of departure, that let compatible hardware triangulate the precise direction a Bluetooth signal was coming from. Typical accuracy landed within about 3 feet. In purpose-built deployments with multiple antennas, accuracy could get down to about 4 inches. That opened up real-time location services indoors, asset tracking in hospitals, indoor navigation in large warehouses, tracking tools or equipment on job sites. GPS does not work well indoors. Bluetooth 5.1 was the first version that could. Now we get to Bluetooth 5.2, released in 2020. And this is the one that matters more than any version since 4.0. Not for speed, not for range. For audio, for most of Bluetooth's history, wireless audio ran over classic Bluetooth. And for audio streaming, classic Bluetooth used a codec called SBC, subband coding. SBC was defined in 2003. It tops out at 328 kilobits per second. It has latency between 100 and 220 milliseconds. Every Bluetooth audio device on Earth is required to support SBC as the minimum baseline. It is baked into the spec. You cannot sell a Bluetooth audio device without it. 2 decades later, SBC is still the floor. Think about that. The codec setting the minimum quality standard for wireless audio in your earbuds right now was designed before YouTube existed. Bluetooth 5.2 introduced LE Audio, a completely new audio architecture built on BLE instead of classic Bluetooth. And with it came a new codec called LC3, Low Complexity Communication Codec. Here is the part that genuinely surprises people. LC3 at 160 kilobits per second delivers audio quality that is roughly equivalent to, and in listening tests, sometimes better than, SBC at 328 kilobits per second. Half the data. Better result. The math works because LC3 runs a more modern compression algorithm that extracts more quality per bit. It also brings latency down to under 10 milliseconds in optimized setups. Barely perceptible. LE Audio also introduced synchronized multi-stream audio, the ability to send separate audio streams to left and right earbuds at the same time, rather than one earbud relaying audio to the other. Earbuds with that support hold more stable, independent connections because of it. And it laid the groundwork for something called Auracast. Auracast was announced in 2022 and has been rolling out since 2024. It is a broadcast audio mode, and explaining it requires stepping back for a second. Regular Bluetooth audio is a point-to-point connection. Your phone pairs with your earbuds. One source, one receiver. Auracast breaks that model entirely. With Auracast, one transmitter can broadcast audio to an unlimited number of receivers at once. No pairing required. The receivers just tune in, like picking up a radio station. Range reaches up to about 330 feet. Think about what this replaces. Airports, train stations, stadiums, and theaters use a technology called hearing loop induction, a wire loop installed in the floor or walls that broadcasts audio magnetically to hearing aids. It is expensive to install, expensive to maintain, and room-specific. Auracast does the same thing in software, from any compatible PA system, picked up by any compatible hearing aid, earbud, or phone. Silent gyms where you tune into the TV audio with your own earbuds. Live music venues with personal audio streams. Airport gate announcements in your own language. A single Bluetooth transmitter replacing an FM assistive listening system. That is where Auracast is heading. The shift is bigger than most people expect. Bluetooth 5.3 in 2021 and 5.4 in 2023 were more incremental, but they introduced things worth knowing about. 5.3 added connection subrating, a mechanism that lets a connected device quickly switch between high-frequency check-ins and low-frequency ones depending on what it needs to do. Real-time gaming controllers need fast updates. A sensor waiting for a button press does not. Subrating lets the device adjust on the fly without dropping the connection. Lower latency when you need it, lower power when you do not. 5.4 introduced periodic advertising with responses, or power, built specifically for one problem: large-scale retail. Electronic shelf labels, those small digital price displays you see in modern grocery stores, need to be updated constantly, across thousands of units, with a two-way confirmation that the update was received. Power lets a single hub push updates to thousands of devices in a structured, low-power broadcast cycle. An entire store of shelf labels, updated at once, each one confirming receipt. That required a protocol specifically designed for it. Bluetooth 6.0, released in 2024, brought the most precise distance measurement Bluetooth has ever had. The feature is called channel sounding. It uses phase-based ranging, measuring the phase difference of signals bouncing between two devices, to calculate distance with accuracy down to about 4 inches. Significant for keyless entry. Your phone sitting in your pocket is close enough to unlock your car. But if someone runs a relay attack, where two attackers relay your phone's signal across a parking lot to a thief at your car, the car thinks your phone is nearby even when it is not. Channel sounding catches that. It measures the actual physical distance, not just signal strength. The difference between your phone being 3 feet away and 300 feet away becomes detectable. 6.0 also added decision-based advertising filtering, which lets a device pre-filter incoming Bluetooth advertisements locally without waking the main processor. Scanning for nearby devices normally triggers constant CPU wake-ups. Moving that filtering work into the radio hardware cuts both latency and battery drain. Bluetooth 6.1, finalized in 2025, made one focused improvement. Random address changes can now happen directly on the Bluetooth controller without involving the host processor at all. The outcome is straightforward. Privacy protection, the rotating address feature from 4.2, now runs faster, with less power overhead, and with simpler implementation for device manufacturers. There is one more chapter to this story, and it is the uncomfortable one. Blueborn. In 2017, a security research firm called Armis discovered 8 vulnerabilities across every major platform: Windows, Linux, Android, iOS. 8 separate attack paths. And what made Blueborn different from every other Bluetooth security story was this: the attacker did not need you to do anything. No prompt to accept, no pairing request, no link to click. Bluetooth on, attacker in range. Your device was exposed. 5.3 billion devices were at risk. 2 years later, KNOB, Key Negotiation of Bluetooth, showed that an attacker could force 2 devices to negotiate a 1-byte encryption key during pairing. A one-byte key gets brute-forced in milliseconds, patched via OS updates, but unpatched devices stay exposed. In 2020, BIOS, Bluetooth impersonation attack, showed that an attacker could impersonate a previously paired device and bypass authentication entirely. All three required OS patches. Stop receiving updates, and the vulnerability stays open. The practical takeaway is not to stop using Bluetooth. 2 habits. Keep your devices updated, and when you are somewhere public that you do not trust, turn Bluetooth off. Discovery mode is the biggest exposure window. So here is where this lands. In 1999, Bluetooth was a struggling short-range radio with a Viking codename and a serious pairing problem. Today, 6.7 billion Bluetooth devices ship every single year. The market was worth over $7 billion in 2024 and is projected to hit $28 billion by 2033. The technology went from 2 phones from the same company cannot reliably connect, to a system that can track your location indoors to within 4 inches, run sensors for 2 years without changing a battery, broadcast audio to an entire stadium at once, and do all of it from a chip smaller than your fingernail. The version number on your device matters more than most people realize. A device running Bluetooth 4.0 and a device running Bluetooth 5.2 are having completely different conversations with the world around them. And the codec your earbuds are using right now, chances are it is still SBC, still 2003, still the mandatory floor. That shifts as LC3 devices become more common. But for most people, the audio upgrade is still sitting just around the corner. Here is the question I want you to sit with. Next time you connect something wirelessly, which version of Bluetooth is it actually running? Because the gap between versions is real, and now you know exactly what that gap looks like. Drop your device and its Bluetooth version in the comments. I am genuinely curious how spread out the audience is across 4.0, 5.0, and the newer specs. If this cleared up something you have wondered about for a while, the like button helps this reach people who are just as curious as you are. Share it with someone who has ever asked you, why does Bluetooth keep dropping? Because now you can tell them. And subscribe if you want to be here for the next one, because we are going full detail on Wi-Fi 7, and what you find out about how your router actually works is going to genuinely surprise you.